Let's look at this reaction one more time, but this time let's make the second step the slow step. First step is going to be the fast step. Now, just like before, the slow step is going to be the rate determining step. So we'd initially write the rate law of this mechanism equal to the rate determining step, which would be first order with respect to NO3 and first order with respect to NO. Problem here is that NO3 is an intermediate. And intermediates typically aren't written as part of your overall rate law. Overall rate laws are usually with respect to the reactants only. So if we want to really find out the mechanism or the rate law for this mechanism, we need to find a way to get rid of the intermediate in this equation. And to do that, we go back to the first step, which again is the faster of the two. Typically what happens is that a fast first step starts to react in reverse, and it will eventually establish an equilibrium. Equilibrium means that both directions are occurring at the same rate. So the forward reaction is again NO and O2 to give you NO3. The rate law of the forward of step 1 would be first order with respect to NO and first order with respect to O2. The reverse of this step is NO3 gives you NO and O2. So in the reverse, NO3 is the reactant. So the rate law of the reverse of step 1 is first order with respect to NO3. Now remember, equilibrium means that the rates are equal. The forward and reverse reaction are occurring at the same rate. So if both of these are equal to the same rate, the same value, if they're equal to the same thing, they're equal to each other. So we can put the two together, and to differentiate between these two k's, we'll call that one k1 and the other one k minus 1. So all of this would be equal to k minus 1 times NO3. And if we rewrite this equation, where NO3 is by itself, we get this. So if NO3 is equal to all of this, we can plug that in to the rate law of our rate determining step. And again, we'll call this K2 since we call the others K1s. So plug that all into our second rate law. So all that is for NO3. We can clean this equation up a little bit. Take all these K's, all these constants, and put them into one value we'll just call K. And we have NO times O2 times NO. We can rewrite that as NO squared times O2. So now we have a better rate law because now we only have our reactants shown in the equation. So as you can see, when the second step is your rate determining step, or any case where the rate determining step isn't your first step, that's going to be a tad bit more involved than what we saw previously, typically because you're going to have an intermediate from a prior step. But if you use the fact that the first step is in equilibrium, coupled with a little bit of algebraic trickery, you can come up with a way to get rid of the intermediate and get you an equation that would look something like this.